Since it was such a long example, let's review the process that we took in solving the linear system of differential equations y prime equals -2, -3, 3, -2 times y. We started by finding the characteristic equation. 0 equals the determinant of a minus lambda I, which was lambda squared plus 4 lambda plus 13. This started out the same as all of the other examples that we've done. Where it was different is when we solved this characteristic equation, we got complex eigenvalues, -2 plus or minus 3i. So using one of these eigenvalues, and it didn't matter which one we picked, but we chose lambda 1 to be -2 plus 3i, we found the eigenvector I1. With our eigenvalue, -2 plus 3i, and our eigenvector, I1, we built a complex solution, yc of t equals e to the -2 plus 3it times I1. We then needed to write yc in its real and imaginary parts. So we wanted to write it as yc of t equals yr plus I times yi. Because then we had a theorem that said yr and yi will both be real valued solutions to the original differential equation. And thus, with these two distinct solutions, we will be able to build a general solution y of t equals c1 times yr plus c2 times yi. So the crux of what we needed to do was to write our complex solution yc in terms of its real and imaginary parts, yr plus I times yi. To write yc this way, we needed to split up the eigenvector into its real and imaginary parts, and then use Euler's formula to split up e to the -2it as e to the -2t times cosine 3t plus I times e to the -2t sine 3t. And then distributing in our multiplication e to the -2 plus 3it times I1 with both factors in the real and imaginary parts, we were able to write yc in its real and imaginary parts to then find the general solution. We will need to follow this same process for other linear systems of differential equations where the characteristic equation has complex eigenvalues.